So, good evening. Let's start today's class. So, I hope my screen is visible. So, today is the class about momentum flux. Till now, we have learned about the mass flux in the last two lectures. So, today is all about the momentum flux. So, what is momentum? When mass is multiplied by velocity, it's called momentum, right? So, momentum is mass into velocity, right? It is m into v. And what is mass flux? So mass flux, we have learned that it is the mass exchanged. It is the amount of mass by per unit area and per unit time. Similarly, momentum flux is momentum calculated divided by time into area, right? So mass flux is about that how the mass transfer happens in a system, how a concentration is changing in a system. Suppose there is an reaction happening in your body, so how that reaction is changing with time and with concentration. That parameter is calculated by the mass flux or mass transfer related all the parameters what we have learned. But in today's lecture or for today or probably next week also, we'll be learning momentum flux. So momentum flux talks about that how the fluid motion is happening. So it is more about the fluid property or convection property. So what is fluid? You know that there's three matter, three sets of matter: solid, liquid, and gas. So fluid can be liquid, either liquid or gas also. Okay. So for the fluid, we take two assumptions. We take two basic assumptions. I think I have gone through this, but again I am repeating it. So first one is the continuum approach, right? Continuum assumption. Second one is the no slip boundary condition. So I think you have remembered what is continuum approach, right? So in the continuum case, fluid is considered as a continuous medium. That means we are considering that there is no molecular spacing. in the field, right? That means we are not considering the individual molecules here. So if you want to consider the individual molecule, that is a different phenomena or different level study where you have to consider the basic molecular property or atomic property. But in the case of, we want to know the bulk motion, basically. We want to know the behavior of the bulk motion, right? So there, how the each molecule changes, how the properties of each molecule is affecting the fluid, that is not that much important, because we are measuring here overall thing. That is why this approach is, this continuum assumption you have to take, otherwise it you cannot get analytical solution very easily. So here, when we can apply suppose our system, so that the system has a characteristic length which is called L. So the characteristic length of the system is L. So it has to be greater than the mean free path distance of the constituent molecules. You can call it as lambda. So in the first class itself, I have told you what is mean free path. It is the distance between two molecules before it collides with each other, right? So this distance has to be very less the characteristic length of a system. Suppose we are considering a pipe flow, or we are considering a blood flow in our body. So here the length of the blood channel, or whatever is the characteristic length, even the diameter of the blood vein, it has to be greater than the molecule. Okay, so this is the continuum example or assumption. Second one is the no slip boundary condition. So no slip boundary condition means the relative velocity between the solid in contact with the fluid and the fluid and the fluid layer adjacent to the solid has to be 0. That means, suppose this is a plate, okay, and the fluid is flowing, okay, a fluid is flowing like this. Suppose this is a fluid and the fluid is flowing like this, and so the bottommost layer, which is actually in touch with the solid substrate, we have to consider that the relative velocity between the bottommost layer and the substrate has to be 0. Okay, so we are considering it like this. So that's why we tell that at this bottom level, that means suppose this is Z, or yes, you can say it like this is X direction, this is Z direction. So this is Z at this point, right? At this point, that means at Z equals to 0, the velocity of the fluid, that is U, is 0. So this boundary condition you have to take it, okay, when the fluid is stable. But if the bottom layer also is moving with a speed or with a velocity u, then you have to take the velocity of the bottommost layer fluid also is u. So here you have to take at z equals to 0, u equals to u. So the relative velocity between these 2 points is 0. So if the plate is in stationary position, you have to take the velocity is 0, and you have to, if it is in motion, you have to take it the velocity of that fluid. Okay, so this is the two basic important assumption for the fluid layer, for the fluid calculation. Next, we will learn different types of fluids. Okay. So one by one I will tell. So first one is the path line. So what is this path line? So suppose this is the actual, this means the definition of path line in a fluid system is actual trajectory followed by a fluid particle. Okay, suppose a fluid is passing and we are giving a particle here, and we are observing that particle, how it is changing its position, right? So that fluid particle will go like this or probably this, whatever it is, depending on the system. So that trajectory it will create, that the path it will create is called the path line in a fluid. Okay. So how we generally define path line? It is basically the velocity of the particle. So we define it at dx dt equals to u, then dy dt equals to v. The position of the particle in the x direction with respect to time is u. Then the change in y with respect to time is v, and change in z with respect to time is w. Okay. Suppose at t equals to 0 time, particle position is x equals to x0, y equals to y0, and z equals to z0. Then we will define it, the particle motion, as a function of x, y, z equals to 0, right? Now suppose I am giving an example. So suppose the particles, there is a particle this, and each has a velocity ax I cap is a unit vector, and minus aay j cap, right? And its positions at t equals to 0 is x equals to x0 and y equals to y0. Okay. So now if we apply the formula, we'll see that dx dt. So what is dx? So this is our x, right? This is our y. So our dx dt is ax, right? The velocity component, this is the u, this is the v, right? So the dx dt would be ax and dy dt will be minus ay. Right now, if we integrate, we will get the expression of x. So x will be, if you integrate and put the value of at t equals to 0, it will come as x equals to x0 e to the power at and y equals to y0 e to the power at. Right? And if you multiply these two, so it will come as a constant. If you multiply these two, minus 80, sorry, it will be minus 80. So if you multiply this two, it will come as xy equals to x0, y0 equals to constant. Right? So that will lead to the your path line expression, that the position at the xy is always, but if you multiply the position of the coordinate of the particle, it will always come to a constant. Next one is the streamline. Next one is the streamline. Streamline is a line in the flow field to which the local velocity vector is always tangential. A line in the flow field to which the local velocity vector is always tangential. Okay, what does it mean? Suppose there is a fluid. Suppose we are taking a line like this. Okay. The fluid path is dr. Okay. And if you take a tangent here, it is the velocity vector of this. Right? So a line in the flow field to which the velocity vector is always tangential. So if it is a flow field in which whether we want to draw, that doesn't matter. So it is the flow field, it has a direction, and it's that the velocity vector is always tangential to that. So from there, what we can conclude that dr cross v equals to 0. These are obviously vector. Okay. Dr cross, because this the velocity component and the flow component, the line component is always tangential. That is why their cross products will be always 0. So what we can conclude from here? So if we express this, it will be I cap, j cap, k cap. dr is dx, dy, dz, and v is u, v, w. This equals to 0, right? So from here you can condition it like dx by u equals to dy by v equals to dz by w. Okay. So this is your condition for a flow to be streamlined. Okay. And now if you take the same example like the previous one, where velocity is ax I cap minus ay j cap. So here, so dx by ax, it is u, and it is v, right? So dx by ax equals to dy by minus ay, right? So what it is coming? If you integrate it, it will come as ln x by x naught equals to ln y naught by y, right? Now if you take out the ln, it will come as xy equals to x naught, y naught equals to constant. So it is same as, its expression is same as path length, right? Now there are more types of fluid that I will come later. First, let's talk about that what is stress or shear stress. So there are two types of stress. One is the normal stress and one is the shear stress or tangential stress. Suppose there is a box or particle, whatever it is, and we are pushing it like this. So this is your normal stress, right? And now if you are pushing the particle or box, whatever it is, from this position or from this position, so that means you are pushing it tangentially, right? So this is called the shear stress. Okay. Now you have seen that shear stress is a second, in the lecture you have seen that shear stress is a second order tensor, right? It is a second order tensor. That means it has two components. So generally we are defining at tau yx. You can define it whether way you want. It is the naming is not mandatory, obviously. So what does they represent? So y represent the direction of area on which the stress is applied. Okay, and x defines the direction of the force or stress, whatever it is. But force and stress are not definitely same, obviously. Okay, so stress is related to pressure, and how pressure is related to force? It is the force per unit area. Okay, so it is the area direction. Why? The first component, suppose there is tau ij. So this I component is decided based on which area the force is applied, and the j component, which is the x here, it will be decided by in which direction the force is applied. Okay, so suppose this is our system, right? So if you notice carefully, what you can tell from it. So what is the I component? Suppose this is my x and this is my y, right? So if you think it as a, so this is x, this is X, and this is Y. So in which area it is working? So the stress is working here, right? On the Y direction. Is it clear? The stress is working on Y area, right? This area, the stress is working. But the direction of the force is X. That is fine. But the change in area or whatever the change will be happening, it will be happening in the position of Y. Suppose if we are giving stress in the X direction, what can be changed? So this position can be diverted to this position. And now the system may be like this, right? Because we have given the stress in this direction. So the stress direction or the force direction is in the X, but the change happens in the Y direction, right? So that is why Y direction or Y area, if it is a 3D space, it will be area. I am showing in a 2D case, that's why I am telling it as distance. So the change happens in the aerial direction and the force happening in the X direction, right? So this is how it is defined. So I component will be telling the area direction and J component will be telling your force direction, right? So from there we have seen that force is so same example if we take and we are giving the stress, right? So it has some kind of angle and this is the position at t equals to 0 and this is the position at t equals to t1 suppose, right? And the angle changed theta, right? So due to stress, so tau yx or you can call it tau, there is some change in the system. So when there are two things. So when if it is a fluid, so we'll call it like it is proportional to theta. Okay, that is your strain. This is your strain and this is your stress. So suppose there is a semi-solid thing, okay, and you are pushing it from the top and the top level is little bit shifted. So, but it is solid after all, so you can conclude that stress is proportional to strain, okay. But in case of solid, but when we are taking fluid, right? When we are taking fluid, the definition of fluid actually comes from here that when we are giving a stress to a system, so it is always going to flow away or always going to yield. Okay. Okay. So for the case of fluid, it is the definition of the fluid that when the stress is applied, it is always going to yield, right? But in case of solid, it is not always the case. If you give a stress to a table, it will not immediately move, right? If you need to put some sort of high energy to move it, right? So this is different thing. But in case of fluid, if you push a fluid, it will anyway flow away, right? So for the fluid case, just it is changed. This equation is changed to from stress is proportional to strain to it is changing to stress is proportional to strain rate. So we have already known the value of the importance of rate. So right in the earlier classes. So it is tau yx is proportional to d theta dt. That means that the angle has changed from 0 to theta, right? So how this is changing, how the angle is changing with time, this rate is captured, in the fluid with a proportional of stress. So in case of fluid, we tell it stress is proportional to strain rate, and in case of solid, we tell it that stress is proportional to strain. Okay. So this ultimately this concept is your Newton's law of viscosity. Right? Okay. Now, how the strain rate is related to the velocity gradient, we will see. Okay. Same figure I am drawing, and I am giving some name. Okay, so this is the x direction and this is your y direction. Okay, so the initial point was A, B, C, D. Okay, now I am giving stress in this direction, and now this change to like this. So it has become C dash and it has become D dash, the new points. Okay. So this has the angle. Okay, this also the same angle. So this is CC, sorry. This is CC dash equals to DD dash is equals to delta U into delta T. How this is coming, I am telling. So this is the change in Y I told, right? And this is the angle. So tan theta equals to CC dash or DD dash, whatever it is, and its direction. This is Y, or you can say delta Y, right? So now, as theta is very small, we will write it like, so then it will be tan theta will be theta. So tan theta will come to theta. So we'll write delta theta equals to Cc dash by delta y. So from here Cc dash is coming as delta theta into delta y. Okay. And suppose we are thinking that Cc is the distance, right? And it has a velocity of u, then it has a velocity of u. So Cc will be del u into del t. That means distance will be velocity into time, right? So from there we can conclude that Cc dash, which is equal to dd dash, is equal to the velocity of the system into time. So you can write it as del u delta u in delta t. And also Cc dash is delta theta into delta y. From the angle trigonometric thing we have proved. So what is coming now, we can just cross check it. Now cross it. So it will be du dy equals to d theta dy. D theta dt, sorry. Yeah, right? So in the earlier case we have seen that tau yx is proportional to d theta dy. That means tau yx is proportional to du dy also, which is the gradient change, which is the velocity gradient. That means the change in velocity in the x direction, because the force is applied in the x direction. That means how the force is changing in the x direction, that is calculated by du, and it is the area is in the y direction, right? We have said that tau yx means, so y is the areal direction. So how this u directional velocity changes, x directional velocity change is happening with respect to the y direction or y opposite direction or perpendicular direction area, right? So this is the concept. So from here the Newton's law of viscosity comes that tau yx equals to, we have to take a proportionality constant and we'll write it like mu du dy, right? So this is your final Newton's law. Okay. Now so the fluid follows, so the fluid follows this Newton's law of viscosity are called Newtonian fluid. But there are some other kind of fluid also, like blood. Blood is not Newtonian, but in some cases it also. But so there are two types of, another type of fluid also comes, which is non-Newtonian fluids. So mostly biological fluids are non-Newtonian fluids. Okay, and it has two branches. One is time independent and another one is time dependent. Okay. So in the case of time independent, so tau x is a function of the velocity gradient. Okay. And here tau x is the function of the velocity gradient plus time. Okay. And it has some subclasses. So you'll see here. So for the time independent cases, we call it power law fluid. What is the expression? So tau ix equals to k into dy to the power n. Okay. N is the flow behavior index and k is the consistency index. Okay. Now what we can write? We can write it tau ix equals to k into dy du dy n to the power minus 1 into du dy, right? We can write it like this. So now this whole thing becomes the apparent viscosity, mu f into du dy. Now it comes to the form of Newtonian fluid, but here mu is not just a simple value, it has to be calculated like this and it is called apparent viscosity. Okay. Now comes the next division. So when apparent viscosity decreases with increasing velocity gradient, okay, then n becomes less than 1. So you have seen the n, right? So here in the apparent viscosity there is n, right? So when n is less than 1, apparent viscosity decreases and velocity gradient increases. So this type of fluid is called pseudoplastic. What are the example of it? The example is polymer solution. They are also called shear thinning fluid. Okay. Okay, so eta is basically the mu apparent. So you can name it as mu apparent also. Same thing. Du dy. Okay. So when the viscosity decreases with increase in the velocity gradient, that is called the shear thinning fluid. The second one is the when eta increases with velocity gradient and n becomes greater than 1, this is called dilatant fluid. The example is sand suspension, right? That means if you create a higher velocity gradient, suppose you are rotating a glass of water, or you have seen in near sand, right? So when if you want to go very fast, the sand and water, sand suspension, if you take, you will see that if you create a higher velocity gradient, there the viscosity will increase. So that is the example of so it is dilatant fluid and it is a shear thickening fluid. Okay, so the third one is the Bingham plastic fluid. We have seen that it has some sort of stress. It has to give some sort of stress, and after that it will behave like a Newtonian fluid. Okay, so the example is paste, you can say, right? Because you have seen, right, in everyday life, if you make your paste tube upside down, it will not automatically come out. You have to give some sort of pressure, then only that comes out, right? So this is the example of Bingham plastic toothpaste. So what our expression is tau ix tau 0 plus mu p du dy. Yeah. So this is the Bingham plastic. And now the time dependent one. So what are the time dependent ones? So in case of time dependent, the viscosity, first one is the apparent viscosity decreases with increase in time. Okay. And second one is the apparent viscosity increases with time t. The first one is called the thixotropic and second one is called the rheopectic. Thixotropic and the second one is called the rheopectic fluid. And what are the example? This is the example. The example is paint, which you put on the walls of your house, and this is the bentonite solution. Bentonite solution. Okay. So, and there is a curve. So, if you want to draw stress versus velocity gradient curve, the slope, the line passing through the origin will be for Newtonian fluid, right? For the Bingham plastic fluid, because after the tau 0, it is going to have a Newtonian like behavior, right? So it is Bingham plastic. And we said that this one is the shear thinning. That means shear thinning, that means velocity is, viscosity is reducing. The slope is reducing with time. So shear thinning is happening. So it is your pseudo plastic, and the opposite case, the shear thickening. So the viscosity is increasing with time. This is your Dialecton fluid, right? And if you want to put this apparent viscosity or viscosity versus gradient, so you can see from the Newtonian fluid, it is just a straight line, right? It is just a straight line for Newtonian. And for pseudoplastic, it is reducing. And for dilatant, it is increasing like this. Okay, remember the graphs because, and also understand the graphs because the question may ask come from these graphs also in your, if you are giving GATE or something, some competitive exam like that, it will come, it will definitely come. So there are some other things also for the equation of momentum equation like this. So we are not going that way much. So I am just finally writing the expression for Navier-Stokes equation. How this is coming, you have already seen in your in the lecture notes. So please go through that. That is already very well explained. I am not repeating it much because I don't have much time. I don't have much time. I have to complete the other equations also. Okay, so you need to do this by yourself. You solve it by yourself. I am going to jump to the final equations of Navier-Stokes, okay, which is the main thing for fluids. Okay. Okay, so this meeting will end in 12 minutes. So I have to make a new meeting. Then just a minute, let me make a new meeting. Okay, so I am giving in the chat the meeting link. So please join there. Okay. Okay. Please join there. I am ending this meeting. So here I am sharing again. So you will get to see. Yeah, I have my screen is visible. Yeah. So in the mass flux or mass transfer case, you have seen the main equation is dependent on the Fick's law, right? Similarly, in the case of momentum flux, there is two sets of equations, Navier-Stokes equations. Okay. First one is the continuity equation. So about the continuity equation, I have discussed in the second class already. If you forget, please go back to the lecture. Okay, so here it is just simply without you considering it is a compressible fluid, it is del cross V equals to 0. And for the momentum balance equation, this is the full equation. Del rho del T plus V dot grad V equals to minus del P del, you can say it X or whatever it is, grad P better to write. Del P del X is for the x directional, so better to write grad P, it is more common, plus mu grad square V plus an external force term or external potential. Okay, so if your external potential is, here has to be a rho obviously, yeah, if it is like gravity something, so you can write in place of FET, you can write it as rho G. Okay, so this is your final Navier-Stokes equation. What does this mean? So this talks about, 1 minute, this is the local acceleration term. Okay, this is convective acceleration term. This is your pressure gradient. This incorporates your viscous term or stress term, viscous term, because you have seen that how stress is related to viscosity, right? Just now from the Newton's law of viscosity. So it is the viscous term or stress term, and this is the external force term. So this external force can be of anything depending on the system. So it can be gravity, gravitational force, right? It can be van der Waals force. It can be some kind of electric force. If your fluid or if your system is an electric medium, so electric field will be the external force. Then the magnetic field can be the external force. Okay, like that. There are other things also. I am talking about the main things. Okay. So this is the basic momentum equation. Okay. So now we'll go to the question answer session. Okay. And we will do accordingly. If some equation we need to solve, we will do there. Okay. So let's start. So do the first question you do. I have just told this. What does it represent? Tell me, what is shear stress? Represents phi tau yx. So that we have discussed this. So you have to be able to, you have to Very carefully see. So we have just said that stress acting along x direction due to the movement of the fluid in the y direction. Stress acting along y direction due to the movement of the fluid in x direction. Stress due to component y on x. Stress acting along z direction due to movement of the fluid in y direction. What is the real answer, you think? So we have discussed it. What is it? Tell me. You take your time and tell me. So the right answer is stress is acting along the x direction, right? We have said this. So stress, so tau yx, we have seen with the example of cube, right? Stress is acting on the x direction, but it is hello. Okay. So this is, so first one is the first option. In the second case, the second equation, Newton's law of viscosity gives a relationship between shear stress and shear rate. That is what we have seen, right? The third question, the fluid that does not flow until a certain minimum shear stress tau naught. So we have seen this example of paste, right? Toothpaste. But it is also true in case of your cream we use, right? So it is the Bingham plastic. Next. A fluid flow in a pipe is characterized by a Reynolds number of 1800. Identify the type of flow. So, for pipe flow, we know from the lecture that when Reynolds number is less than 2100, it is laminar flow. When it is greater than 4000, it is turbulent flow. And when it is in between laminar flow and turbulent flow, it is transitional flow, right? So what is this Reynolds number? It is the dimensionless number of inertial force versus viscous force. And it is defined, its formula is rho Vd by mu. Rho is the density of the fluid, V is the velocity of the fluid, D is the characteristic length of the fluid, mu is the viscosity of the fluid. Right? So this is the option for laminar. So it is told 1800, right? In the presence of external forces, the rate of change of momentum in the direction of motion is dependent on forces in the direction of motion. Okay. Next. Equation of continuity for momentum transfer. So in the equation of continuity you have derived in the second class probably, or your first class. If you forget this, go back to that class and check. So it is that d rho dt, total derivative of density, equals to minus rho into divergence of V. Next, for a flow in a falling film of fluid over an inclined surface, which is influenced only by gravitational forces from exterior, the shear stress distribution is rho gx cos beta. So it is already done. Next. The rate of change of momentum per unit volume is given by the vectorial equation this. Here is the term. So in the Navier-Stokes equation I have shown you. So this is the most expressed term, right? But this is coming from the stress term. We have seen that viscous term or the stress term, right? So this is related to here. So it is asked about this term. So it is the rate of gain in momentum by convection per unit volume, rate of gain in momentum by viscous effects per unit volume, pressure force on the element per unit volume, gravitational force on the element per unit volume. So it is the stress term or viscous term, right? So it will be option B, rate of gain in momentum by viscous effects. So this divergence of tau will ultimately changes to the form that I have written mu grad square V, right? Right. Next, which of the following is the Navier-Stokes equation for Newtonian fluid? Tell me. So originally it is like this. So I have whatever I have written, it is in this form for incompressible fluid. So why? Because now you can see that rho has come out, right? If it is not incompressible, rho cannot be come out like that. So it is option B. Next, which of the following statements is true in flow in a falling film of fluid over an inclined surface? Velocity of the fluid at the liquid-gas interface is the maximum. Velocity of the fluid at the liquid-solid interface is the maximum. Shear stress at the gas-liquid interface is minimum. Shear stress at the gas-liquid interface is the maximum. So, this is your substrate, right? And fluid is falling. So, this interface is called liquid gas interface, and this interface right here is called the liquid solid interface, right? Now, what do you think? That velocity of the fluid at the liquid gas interface is the maximum, right? Because here it is the velocity is like velocity is facing a resistance because of the substrate, right? Because of the friction with the substrate. So the velocity cannot be high there. So it is the first option. Velocity of the fluid at the liquid gas interface is the maximum. Another one is true. So when the velocity is high, so it has a velocity profile like this, right? So here the velocity is maximum at the liquid gas interface, and also as the velocity is high, that means shear stress has to be minimum. So option 3 is also correct. So shear stress is maximum in this position, right? So shear stress, if you want to draw the shear stress curve, it will be like this. Like this. The shear stress is maximum in the liquid solid interface. Okay. Next, identify the types of fluid from the graph below. So it is very easy. I have shown you like this, right? So A is your Newtonian fluid. B is your Bingham plastic fluid, right? C is your shear thinning fluid, that is pseudoplastic fluid, right? Because you can see here the slope is reducing, so it is shear thinning. So it is pseudoplastic, and this is shear thickening, this is dielectric. Option D. Next. From below, identify the power law fluid with viscosity dependent on its shear rate. So when the viscosity is dependent on the shear rate, that means viscosity is changing with the shear rate, viscosity is increasing with the shear rate. So we have seen that it is the dilated fluid, right? Because the other options are not true here. Newtonian fluid is not, Bingham plastic is not, water is one kind of Newtonian fluid. Okay. Next. A fluid flow in a pipe is characterized by a Reynolds number of 4520. Identify the type of flow. So I have told you that for pipe flow only, the regime is defined like for laminar it is less than 200, and for turbulent it is greater than 4000. So it is 4520, so it is obviously turbulent. Next. In the presence of external forces, the rate of change of momentum in the direction of motion is dependent on the forces in the direction of motion. Select the correct statement. So the above statement is true, right? So in the presence of external forces, the rate of change of momentum in the direction of motion is obviously dependent on the forces direction of motion. So it is true. Next. Define the Reynolds number. I have shown you. So it is rho Vd by mu. So it is option 3. Next. Shear stress is momentum flux, momentum rate, or whatever. So now we have to calculate the unit. So shear stress, I have said you shear stress is nothing but the pressure. So pressure is force per unit area. So shear stress unit is kg meter force per unit area, right? So force is mass into acceleration. So mass into acceleration meter per second square by meter square, right? So it is kg per meter second square. And what is the momentum flux unit? So momentum flux is momentum by per unit area. So momentum is mass into volume. For momentum flux, let's do. Momentum flux is mass into velocity, meter per second, right? Per unit area, meter square, and per unit time. So it is coming as same, kg per meter second square, right? What is momentum rate now if you check? So momentum rate is momentum, that is kg into velocity. Rate means per unit time. So it is kg meter per second square. No, the true is kg per meter second square. It is momentum flux, right? Next. The rate of change in momentum per unit volume is given by the vectorial equation. So what is the term? So I have said you the first term is about the local acceleration. Second term is about the rate of gain in momentum by convection. So it is the rate of gain in momentum by convection. Because why, if you don't remember the term expression also, you can say that it is like it is constituting the velocity and convection term. Why? Because it includes the velocity term. The velocity means it is considering the bulk velocity motion. Okay. Next. Which of the following is the Euler equation in Newtonian fluid? So, the equation we have seen, right, in the Navier-Stokes equation, dt minus grad P plus mu V plus rho G. Okay. So now in Euler equation, this viscous term will be absent. So rho dV dt equals to minus grad P plus rho G. Right? So it is option A. Next. Identify from below the suitable boundary conditions for a flow in a falling film over of fluid over an inclined surface. X equal to 0 is the liquid gas interface. So this is the falling film. Okay. And this is your X and this is your, sorry, this is your X, this is your Z, right? And this is X0. So X0 is the liquid gas. So this is at X0 and X equals to delta is the solid fluid interface, right? So what will be the case? So at X equals to 0, Vz equals to 0. So at X equals to 0, tau Xz will be 0 because I have shown you earlier that the stress will be minimum at the liquid gas interface, which is X equals to 0. It is option B. Third one, X equals to delta V equals to V max at X equals to delta Vz equals to 0 because here no slip boundary condition will be applied, right? Because it is the X equals to delta. Next, which of the following equations correctly express Newton's law of viscosity in one dimension? You think of it and I will give you because it is the easiest. So, if you think of it, so it is also, this can be also true, but actually from the transport phenomena point of view, the answer will be this, option B, because velocity is always going from higher pressure zone to lower pressure zone, right? Higher to lower velocity, and also it is true for the concentration. In the mass transfer equation also you have seen that we are always considering a minus d, right? So it is like this. So it is the actual one. Right? Next. What are the fundamental dimensions of dynamic viscosity in the mass length system? So now we'll calculate, so we can calculate from the Newton viscosity. So tau x, yx equals to mu du dy, right? So tau we have seen it is the shear stress, right? So it is force per unit area, forces mass into acceleration. So mass into acceleration per unit area, right? Also, you can do it in the mass length system. So it is mass unit acceleration per unit area, right? Equals to mu. Du is the velocity, so it is length per time by 1 by length. Okay, so it is coming as mass L to the power minus 1 and T to the power minus 1. So it is option C. Next. According to the notes, what is the critical Reynolds number upper limit below which the flow in a pipe is guaranteed to be laminar? It is 2100. Next. At a liquid-gas interface under standard non-turbulent condition, what is the primary boundary condition assumed for the shear stress or momentum flux? So, at the liquid-gas interface, so the velocity will be higher and that means there will be no gradient, velocity gradient will be 0. That means the momentum flux, that is the shear stress, will be 0. So, it is option C. Next. A Newtonian fluid of density rho and viscosity mu flows down an inclined flat plate at an angle beta to the vertical as a thin film of uniform thickness delta. Derive the expression for the velocity profile starting from the integrated differential equation using the boundary conditions. Calculate the ratio of the average velocity to maximum velocity. Okay. So now the differential equation is given, right? So mu dvz dx equals to the stress is minus rho gx cos beta, right? Now vz equals to minus rho g cos beta by mu, and for x it is 2 into x square plus c, right? Now we are applying the boundary condition that at Vz delta it is 0 because it is the no slip boundary condition, right? So it will be 0 equals to minus rho g cos beta by 2 mu delta square plus c. So what will be the c? Now c will be coming as rho g cos beta by 2 mu into delta square, right? Now if we put this in the equation, so Vz will be so it will be rho g. So for the equation, it will be rho g cos beta by 2 mu delta square minus x square, and we are taking the delta square as common. So rho g delta square cos beta by 2 mu will be 1 by x by delta square. Okay. Okay. So this is the equation, velocity profile. Calculate the ratio of the average velocity to the maximum velocity. Okay. Now we will do the average velocity. Average velocity means Vz will be 1 by delta. So it will have to integrate from 0 to delta Vz dx by, not by because we have taken out the delta, right? So now if you put the value, Vz average 1 by delta so we can take the constant out, which is the rho g delta square cos beta by 2 mu, and here is a delta, so it is delta. So what is left is the Vz dx, right? 1 minus x by delta square. So it is integrating from 0 to delta 1 minus x by delta square dx, right? So if you integrate it, it will be like rho g delta cos beta by 2 mu into, it will be x minus 1 by delta square is the common. So it will be 1 by 3 delta square into x cube, right? 0 to delta. Now if you put the value of delta, it will be coming as rho g delta cos beta by 2 mu into, it will be coming as delta minus delta cube by 3 delta square. So it will be delta minus delta by 3. So if you take the common delta square, it will be 1 minus 1 by 3. So it will be 2 by 3. Okay. And 0 will be cancelled out. Next is the ratio of maximum velocity. So Vz max. So when the Vz will be max? Vz will be max at x equals to 0, right? From the inclined plane problem, you know. So it will be coming as rho g delta square cos beta by 2 mu. Because if you put x equals to 0 here, for maximum velocity, this term will be gone. So only this term will be left. Now what is left? So it is your Vz max. So the ratio is asked for velocity average. So it is Vz average velocity by Vz max. So it is, if you see, the first term, constant terms is the same. So it is only 2 by 3. This is your answer. Okay. Next question. A liquid film of width W, thickness delta, density rho, and viscosity mu flows down a flat plane inclined at beta equals to 60 degree to the vertical. Take G, this, calculate the total volumetric flow rate Q of the liquid in meter cube per second, right? So for flow rate, we need to calculate velocity into area. So velocity is Vz, which is already calculated from the previous problem. Area is W into thickness, width and into thickness, right? So Vz we know. We have to take the average velocity here, so you can write it like this. So average velocity was, the expression is coming like this, right? So 2 if you cancel out, rho g delta square cos beta by 3. So it is rho g delta square cos beta by 3 mu into W into again a delta. So it is delta cube basically. So everything you know. So you just put the value. So rho is 1000, G is 9.81, delta square. Delta is 2 millimeters. So 0.002 cube into cos beta cos 60 degree divided by, there is a W also. So W is 10 centimeters. So 10 into 10 to the power minus 2. So 10 centimeter is 0.1 meter and 3 mu is 0.1. So now if you calculate, you will get. So calculate with me. So 1000 into 9.81 into 0.002 cube into cos 60 into 0.1 by 3 into 0.1. So it is coming as 1.308 1.308 into 10 to the power minus 5 meter cube per second. Okay, this is the answer. Next. For a Newtonian fluid flowing down an inclined plate, what is the shear stress exerted by the fluid on the surface of the plate at x equals to 0? X equal to delta, sorry. So many times I have done this. So it is the rho g delta cos beta. Okay. Next. Where does the fluid achieve its maximum linear velocity? In a uniform falling film on a flat plate. So maximum linear velocity is achieved at x equals to 0, that is the free surface. So option C. Next. In terms of pipe diameter density, how this so it is rho, pipe diameter d, velocity this, average velocity rho v d by mu. So it is option B. Next. If the volumetric flow rate Q of a falling film is doubled while keeping fluid properties rho u and inclination angle constant, by what factor the film thickness does the film thickness delta increase? So we have just seen that Q equals to rho g delta cube cos beta w by 3 mu. So Q is proportional to delta Q. So if it is doubled, right? So it will be per minute. So Q1 by Q2 equals to delta 1 by delta 2. So we need to calculate the delta 2, right? So it will be delta into Q, it is delta 1 cube into delta 2 cube, right? So delta 2 cube will be delta cube into 2 cube by cube. So delta 2 will be, so delta 2 will be 2 to the power 1/3 into delta, right? So it will be 2 to the power 1/3 first. Next, a Newtonian oil with density and viscosity flows down a vertical wall in a uniform film of thickness delta. The wall has a length L and width W. Take G. Determine the shear stress at x equals to 1.5 millimeter halfway through the film. Calculate the total viscous drag force exerted on the fluid exerted by the fluid on the wall surface. So shear stress as x is tau xz equals to rho gx cos beta. Here beta is 0, cos 0 is 1. So it is rho is given 900 into 9.81 into x 1.5 into cos 0. So it is coming as so it is 1.5 into 10 to the power minus 3. So better to write it as 0.0015. Okay. So it is coming as 13.2435 Pascal, right? Next question is calculate the total viscous drag. So total viscous drag force is the shear at wall into its area. So shear at wall means rho g delta cos beta. So here it will be rho g delta, that means rho 900 into 9.81. Here delta would be 3 millimeter. So it is 0.003 into cos 0 degree into A is W into L. So W is 0.5 into 2. So it is coming as, drag force is coming as 26.26.487 Newton, right? Next, an experimental liquid of density rho flows down a flat surface inclined at beta equals to 45 degree to the vertical. The film width is W and the thickness is measured to be delta. A total volume of Q is collected at the outlet. Take G and calculate the dynamic viscosity of the fluid. So for an inclined plane, we know Q equals to rho G delta square cos beta W by 3 mu. Right? So now just put the values of mu and you will get. Mu will be rho G delta square cos beta W by 3Q. It will rho be 1200 into 9.81 into 0.0015 Q. Yes, it is cube. Sorry, it is cube into cos 45 into W is 0.2 divided by 3 into Q is 4.5 into 10 to the power minus 6 equal to So it is coming as 0.416 Pascal second. It is a unit of viscosity. Okay. Next. The kinetic energy of a fluid flow per unit time is given by this. The kinetic energy correction factor alpha accounts for non-uniform velocity distribution across the cross-sectional area A and is defined as this. Using the laminar falling film velocity profile, calculate the exact value of alpha. Okay. So, from the falling film case, we know that total area, we can define it as like dA can be defined it as W dx. Total area A is W delta. The average velocity is defined as 2/3 of Vz max, right? Then integrating this Vz cube dA, integrating this, it will be coming as W Vz max cube 0 to delta 1 minus x by delta 1 minus x by delta square cube dx, right? Now you have to just do the mathematics here. So if you take u equals to x by delta, then dx equals to delta du. So we are doing the numerator part first, right? So it's this a. So now we'll putting the values, integration values. So for the integration term, it will be integration of 1 minus x by delta square will be 1 minus u square whole cube del into du. It will be delta du and it will be changed from 0 to 1 because as you have seen that when x equals to 0 equals to 0. When x equals to 0, delta equals to 0. When x equals to delta, u equals to delta. Equals to 1, right? So it is with respect to du, right? So now it is coming as delta will be there 0 to 1, 1 minus 3u square plus 3u to the power 4 minus u to the power 6. Okay, du, right? So now if we do this, So it will be delta. So it will be U means 1 minus 0. So it will be just 1 minus 3 by 3 u cube. I am not writing the term after integration. You just check for example. I am finally putting the values, putting the limits, and finally writing the equations. Okay. Or do I need to write it for you? So if I just write it, so it is u minus 3 by 3 u cube. So it is just u cube plus 3 by 5 u to the power 5 minus 1 by 7 u to the power 7 from 0 to 1. So now if you put the values, so delta will be, it is 1 minus 0, 1 minus 1 minus 0, 1 plus 3 by 5 into plus 3 by 5 minus 1 by 7. So it will be coming as, so it is 35, right? So it is 35 minus 35 will be 0. So it will be basically between 2. 21 minus 5, it is 16 delta. So now what is the upper term? So upper term is coming as WVZ max cube. So upper term is coming as WVZ max cube delta into 16 by 35. So what will be? So it will be 16 by 35 VZ max cube into A, right? And what was the numerator asked? It is the AVZ cube. AVZ cube, right? So denominator, was A average of VZ cube. So A we know VZ cube means 2/3 VZ max cube, right? So it is coming as 8 by 27 VZ max cube into A. Now if you take the ratio of them, you will get the alpha. So now I'm just taking alpha is this by this. So it is 16 by 35 into 27 by 8. So it is 54 by 35, which is around 1.543. Okay, so it is, the ratio is, kinetic factor is, actual kinetic factor, correction factor is 1.543. Next. Consider a non-Newtonian pseudoplastic fluid or the following the Oswald-de power law model, where K is the flow consistency index and n less than 1 is the flow behavior index. The momentum balance on an inclined film yields the shear stress profile tau xz equals to rho gx cos beta. Derive the analytical expression for the velocity profile Vzx in terms of Kn rho g beta and delta. Express the total volumetric flow rate per unit width as a function of film thickness delta. So tau xz is this. So expression we have to write K minus dvz dx to the power n equals to rho gx cos beta. Okay, so minus dvz dx is rho g cos beta by k whole to the power 1 by n into x to the power 1 by n, right? Now if we integrate with the if you integrate, what will come? So it will be vz equals to there will be minus rho g cos beta by k whole to the power 1 by n will be x to the power 1 by n dx. That means x to the power 1 by n plus 1 by 1 by n plus 1. So if we take, so it will come as x to the power 1 by n plus 1 by 1 by n plus 1. So it will be coming as minus rho g plus c. Definitely there will be a constant. Rho g cos beta by k to the power 1 by n, it will be n by n plus 1 into x to the power n plus 1 by n plus c. So now from the inclined plane boundary condition, we know that at x equals to delta, vz equals to 0. So c will be coming as rho g cos beta by k to the power 1 by n into n by n plus 1 into delta to the power n plus 1 by n, right? Now if you write the vz, it will come as vz equals to rho g cos beta by k whole to the power n into n by n plus 1 into delta to the power n plus 1 by n. If you take common, it will come as 1 minus x by delta whole to the power n plus 1 by n. Okay. Now for volumetric flow rate, you have to multiply this with the area, but if you want to take the multiply Q by W, so it will be just 0 to delta Vz dx. Dx is the width. So you have to do the integration and then you will get the final equation. I am not doing it. Okay. Or finally, I can write the expression Q by W is coming as rho G cos beta by K to the power n into n by 2n plus 1 into delta to the power 2n plus 1 by n. Okay, it is just the integration, you do it yourself. A fluid film of thickness delta with W density this and viscosity mu flows down a flat plate. The angle of inclination to the vertical is given by beta. Find the value of beta that maximizes the flow rate down the plate and calculate this maximum mass flow rate in kg. So for the mass flow rate m dot rho into, we know the q, like rho g delta cube cos beta w by 3 mu, right? So to maximize the mass flow rate, beta has to be 0. So for mass flow rate to be maximum, beta has to be 0. Okay, so for that case, m will be because it is in the vertical position. Okay, so m dot will be rho square. Rho square is 1100 square into 9.81 into 0.001 whole cube into cos 0 into 0.5 divided by 3 into 0.05. It is coming as it is coming as 0.0395 kg per second. So this is your answer. So that's all for today. I hope you have understood the transition from concentration gradient to velocity gradient. So here the driving force is the velocity gradient. Earlier it was the concentration gradient. There is so much similarity with the Fick's second law with the Navier-Stokes equation. Also you have found that. And I hope this class will be helpful to do your assignment, this week's assignment. So we'll be meeting on next week, the same time. So till then, goodbye. Thank you for joining.